And, oh, there we go. We're live. Okay. So, vector and parametric forms of the line. In this case, we're just dealing with vector and parametric equations in R2. In other words, in 2 dimensions in real space. So, to get the vector equation of a line, basically we need 2 things. We need a position vector, and a position vector has its tail at the origin, and its head is somewhere, its tip is somewhere out on the Cartesian plane, and then a direction vector that tells us what direction the line is going. We multiply the direction vector by some parameter. In the preamble, we use s, but the parameter can be anything. Often it's t. And we multiply the direction vector by that parameter, vector times a scalar. Basically, we can get almost anywhere on a line. We can get anywhere on a line using that method. Okay, so we're going to start out with this problem. Find the vector equation of the line that goes through A, which is 3, 4, and point B, which is 4, 2. So to have a vector equation of a line, we need 2 things. We need a position vector, and we need a direction vector. All right. Any ideas what a possible position vector might be? Anybody? Anybody? I know Maddie can't talk, so. Okay, so we're going to make a position vector. It's going to have its tail at the origin, and I could pick 4, 2. I could pick 3, 4. I could pick anywhere in between there, but I'm going to pick 3, 4 because that's what I like. Okay, there we go. So here's U, and this is our position vector, and it is at 3, 4. Okay, and we're going to have a resultant vector here. So we're going to start out at 3, 4, and then we're going to go in the direction of 4, 2. So this is our direction vector here. We just have to figure out what the direction vector is. Okay, so this is V, and we're going to find it by taking 4, 2 and subtracting 3, 4 from that. And so our direction vector in this case is 1, negative 2. Okay. Oh, who did that? Who put a result there? Okay. Our resulting vector that we get looks like this. So the resultant is starting at the position 3, 4 plus some parameter s times 1, negative 2. Okay. And you'll see this written in a variety of ways, but this is one form of writing the vector equation of the line. The resultant vector is the position vector plus a parameter times the direction vector, and that will make a line. And as you can see, as we extend, as we multiply this by a scalar, okay, the result could be anywhere on a line that looks something like that. Okay. There's a second form of the line, and that's the parametric form of the line, in which case we express each coordinate using the coordinates of the position vector plus a scalar times the direction vector. Okay, so we can write it this way if we want. X equals 3 plus 1 times s, and y equals 4 minus 2s. Okay, so this is the parametric form.
Unfortunately, today will be an indoor recess. Once again, the recess this morning will be an indoor recess.
All right. Since this is a line, obviously it does have a y equals mx plus b form, okay, because that resultant, the line is going to go through a y-intercept and it's got a slope. In the preamble, we already saw that we can actually look at the slope by taking the rise and dividing it by the run. Just looking at the direction vector, we can see that slope already. To do this, though, we're going to do a little trick, and we're actually going to convert it to something called symmetric form. And we'll have a little bit more about, symmetric form. That's an R in some sort of unholy hybrid with an m, but that's okay. All right, so in symmetric form, basically what we do is we isolate the s, okay? So x minus 3 is equal to s. Also, we can see that y minus 4 divided by negative 2 is equal to s. Okay, so this is the symmetric form of that line. So there's a third form of the line. We've got vector, we have parametric, we have symmetric form of the line. And we've done some exercises where, you know, we calculate what s is based on a value of x. All right. So here we go. X minus 3 is equal to x, and y minus 4 over negative 2 is equal to s. So that means that x minus 3 is equal to y minus 4 over negative 2. And look at that. Already we're going to be able to express y in terms of x just by rearranging this. So my first thing, multiply everything by negative 2. Whoa, that was close. What do I mean was it? It was close. It was terrible. All right. And then I'm going to move the 4 over. And so this becomes negative 2x plus 10. Okay? So we've gone from 2 points to finding a direction and a position vector and getting the vector equation of the line. We've gone from getting that vector equation of the line into the parametric form of the line. We've gone from the parametric form to the symmetric form, and from the symmetric form to the y equals mx plus b form. There can't be any more forms than that. Okay. Last thing that we're going to do, we're going to find out if this is the same line as a second line. So we're going to see if these lines are coincident, because as you can probably see, like we could pick any number of position vectors and we could pick any sort of direction vector that we liked as long as it has the same slope as that line. Okay, so here's our question. Is it the same line as, and I really shouldn't say it's the same line, but I should say, is it coincident with xy equals 5, 0 plus t times negative 3, 6. Okay, and I better write up the original here so that we can see it again. So this is the one we're interested in knowing. This is L2, and this is L1. This is the original one, and it was defined as xy equals 3 floor plus s. I don't know if I used s. No, I used t, but that's okay. We'll learn how to cope. 1, negative 2. Okay. So a couple of things. We have to see if they are the same line or if they are coincident. First of all, they have to be parallel. So the first question is, are these two lines parallel? And to see if they're parallel, basically all we have to do is go to the direction vector of each line and see if they basically have the same slope. Okay. Are they parallel? Anybody? Anybody? So let's look at negative 3, 6. And actually, I can see that I can make negative 3, 6 by multiplying s by negative 3. Okay? So this line is just a scalar. This direction vector is just a scalar multiple of.
Mr. Rogers,
Yes?
can you move the camera to the right a little bit?
Can I?
The
Yes,
last point isn't there.
move it to the right. Okay. Tell me if I get this right. Tell me if I turn horribly white.
Good.
That's it? All
Yep.
right.
What's parametric form? I don't know how you got that.
Okay, so parametric form, just basically we have a formula for the x coordinate, and we have a formula for the y coordinate. Okay? So this is the vector form of our second line, Johnny. If I want to turn it into the parametric form, this is x equals. So our position vector had an x coordinate of 5, so that's where I'm going to start up. And then to get anywhere on the line, I just have to multiply it by -3 times some parameter t. So there is the parametric form for x. Can you tell me what the parametric form of y is for this line, this new line that we're looking at?
6t.
Exactly, yes. Okay. We don't have to put the 0 in there, so it's just 6t. All right. Good so far? Does that make sense? Parametric form? Okay. We have established that those two lines are parallel. So here we go. If they're parallel and they both contain the same point, then these are the same line, essentially. They are coincident with each other. So we have to answer this second question. Do they contain a common point?
Did you just make up those points for the second line, or like where did those ones come from?
Oh, for these? Yeah, I hate to give it away, but in fact, these are the same line. So I just basically picked a second direction vector that's going to get us to the line, and I picked a direction vector that's basically a scalar multiple of this. I chose a point that was also on that line. Okay, but right now you don't know that, so you're through the looking glass.
So,
Okay.
like you would have given us points though to solve it.
Oh yeah, like I would give you the equations of the line.
Okay.
Okay. So basically what I'm going to do is I'm going to see if 3, 4 is contained in this line number 2. Okay. All right. So I'm going to see, does 3, 4, which is the position vector of line 1, lie on L2? Okay. So I could do this a few ways, but basically I'm going to express L2 in its parametric form, and I'm going to find the value of t. I'm going to see if that value of t results in the same x and y coordinate as 3, 4. Okay, so my x coordinate is 3, and I know my formula for that is 5 minus 3t. Okay, now I'm going to isolate t. In other words, I'm going to find the value of t that gives me a 3. So 3 minus 5 is -2. And then I'm going to divide that by -3. And there's my value of t. And since both of those are negative, I'm just going to turn t into a 2/3. Okay. So to get an x coordinate of 3, t has to be 2/3. Now I'm going to find out what the y coordinate is when t is 2/3. And if that y coordinate happens to be 4, then these two lines are going to be coincident. Okay. So I'm going to take the formula for y, which is 6 times t. In other words, 6 times 2/3. Okay. And so 6 times 2 is 12, divided by 3 is 4. And so, yes, 3, 4 lies on the line. Yes, 3, 4, I'm calling you a liar. All right. So that's that.